All right, I am going to your homework. And you said it was on the normal section, so let me go to that. Okay. All right. Now, what kind of calculator are you using?
I have the TI-84 Plus.
Okay, so it should be. I mean, I've got an emulator of this 84 Plus Silver, so it should be fairly similar then. Okay, let me share my screen, and then you can just kind of direct me as far as what problem I'm looking at. So this was your normal homework. I assume I should just go straight to the X's or the blanks.
I think it was number 6. I want to say
6.
it was
Okay.
Yeah.
You got it right. So whatever you did worked.
Some of them I was guessing.
Gotcha.
Yeah.
Okay.
Like that one I didn't know how to get it.
Find the z-score such that the area under the standard normal curve to the right is 0.42. Okay.
Any way you can make it bigger?
Yes. Okay. Sorry. Pull up something I can click on. And then let me full screen this. All right, that better?
Yeah, that's better.
Okay. All right, so the problem says to look at this chart. Although honestly, our calculator can also do this, but we'll go to the chart and we'll see what the chart says. So here is the chart, and I'll make that one bigger. As well. Okay. Now the thing about this chart, though, is when we talk about area underneath the curve and we're measuring, given a z-score, we're trying to find probabilities, it's going to give us the area to the left. So we kind of have to be aware of which direction it's asking versus what direction we want. So if it said find the area under the normal curve to the right of 0.42, let's see, find the z-score such that the area to okay, so if the area to the right is 0.42, then the area to the left should be 1 minus 0.42. So in which case I would just go to my calculator and just do 1 minus 0.42. And so the left-sided area, which this table measures, would be 0.58. So at that point, what I want to do, I don't know if I have the whole, I don't have the whole chart on here, but, and I'll go back and I'll get the other part, but I'm looking for, in this brick of numbers, is something close to 0.58. And so I can see that I don't see it. So I'm just going to go back to my chart, and if I scroll down, I'll get more numbers. And I'll make that one bigger so we can see what it says. Okay, so as I'm looking here, I'm looking for 0.58. I see 0.53, 0.54, 0.55. And I don't get 0.58 till right about here. So between, here's 0.579 and 0.5832. So it's right between these two values. So I need to know what this number is and what this number is. And if I go all the way up to the top of the chart, they tell me that that first column is 0 and that second column is 0.01. Sorry, 0.00 and 0.01. So when I come down here then, the fact that I see it about 0.2 And so it's somewhere between 0.20 and 0.21. And then if I come back up here, that's where they're getting that 0.20 from then.
Oh, well.
Yeah, because they're saying rounded 2 decimal places, and so it's closer to 0.20 than it is to 0.21. So that you would just type in that particular number. Now, your calculator does have what's called an inverse norm feature. So if I go to distributions, which is second, right above vars, so I go second distributions, and then I want inverse norm. Inverse norm says what's the area. So I can type in that 0.58, and it's going to ask for standard deviation and mean. And for z-scores, that's just 0 and 1, so I'm going to keep it like it is. And then I just hit enter, and I can see exactly what the number is. That it's exactly 0.20189, blah, blah, blah. Even though that chart isn't that accurate, I can still see it. And then I just rounded 2 decimal places like it asked me to. So either the chart or inverse norm will get the job done.
Okay.
Okay?
Mm-hmm.
Moving on. So let's see. So that was number 6.
Mm-hmm.
Do you have another request?
Maybe it's 7. It's one with like with an A and then like the number. I need that one too.
Okay. I'll make that bigger. Okay, find the z-scores that separate the middle 64 from the area of the tails. So if I'm looking at the middle 64, what's the area on the tails, if that makes sense? I'm going to go back up to this little pretty picture here. So imagine I'm looking at the middle. This mound is 64% of the data.
Mm-hmm.
So how much is left over? So we just do 100 minus 64. So I got 36% of the data that's got to be in the 2 tails. So if it's symmetrical, then I just want to divide that by 2. So that means I've got 18% of the data in 1 tail. So this picture right here.
Mm-hmm.
Okay. So one way I could do it, since I've got the chart in front of me, I don't know if I've got, let me look here. Oh, I do. Oh, that's nice. Okay. So if I look at the chart, since I'm looking for 0.18, the area to the left, and I just look for the number that's closest to it, and it looks like it's about negative 0.9.
Right.
Actually, as we go here, let's see, so that's negative 9.0, negative 9.1, negative 9.2. So you can see that's one way to get the number. Or, more likely, you can just use the inverse norm part we just did. So I go back to inverse norm, and then just do the 0.18. And then just hit enter. And the calculator will tell me that it's about negative 0.1953, which rounds up to negative 0.92.
Yeah, I think that way is better.
Well, again, there's multiple ways to get the answer. So if you're not sure, you can at least, check the questions that have the chart on them. So, and my feelings are not hurt either way. There used to be I'd say used to be. So before they had the TI-84s, that's how students learn statistics, is they'd go to these charts.
Oh, okay.
And there would be like encyclopedia books of these decimal approximations, so that people could get more and more accurate answers. But aren't we glad there's calculators now?
Mm-hmm.
All right, let me go back here. It would just try 8, see if 8 looks like.
It Is it that one with the A?
It's asking about a critical Z. I'll show it to you.
Yeah, that's the one.
Okay. So this alpha here represents, I mean, we're talking about z-scores here. So it's a z-score related to 0.33. Let me see if we can, I don't think I've got it in the chart here, because I only have so much in this chart. Not really. No, I don't have that part on there. Okay. Let me think. Okay, so in our calculator, actually, let me go back to here. Let me look and see which Z sub alpha is what it's called, yay. And area to the right is the unknown is alpha, so the area to the left is 1 minus alpha. So this number, this 0.33, we want to the left is 1 minus that. So 1 minus 0.33, which is 0.67. I think we'll just inverse norm that. Yeah. Okay. So then we're going to come over here and inverse norm. This is inverse norm. We sure do get a lot of bang for our buck. Does all sorts of cool things. All right. So we got 0.4399. I'm curious, how accurate were they on that?
Yeah.
That rounds to 0.44. Huh. That's irritating. Well, you got it right.
Yeah.
And I mean, on your test, I'd give you credit for it. So, I mean, I do go back and look at what you guys type in. So, huh. There's not too much freedom here. I wonder if that chart, they were basing off the chart. Let's see. No, just inverse norm. Okay. All right. Huh. All right. Well, I'm kind of irritated that there's a decimal off, but I'm not losing sleep over it. Just keep going. You got this one right? You want to look at it, or?
Yeah, you can go ahead. Not the graph part, but the other one, the PX.
Oh, the P. Okay. Oh. Yeah, this is another. Well, that's, you know, our calculator is our friend. Come down here. All right, so assume randomly variables normal, which is how I know I can use norm CDF. They tell me a mean and standard deviation, and they want me to calculate a probability of something being less than or equal to 45 given a 51 and a 7. Okay. So in that case, if I want a probability, that's not norm, that's not inverse norm, that's actually norm CDF.
Right.
So I just go to norm CDF, and it wants, it's going to show the actual picture. Come here, calculator. Okay, so that's this picture that we're doing, and we want this shaded piece. So I need a lower bound, and typically the lower bound is negative infinity on that side. So our calculator sees that as -1e to the 99. And then the upper bound is going to be 45. And I'm going to change the mean and standard deviation to this problem. So a mean of 51 and a standard deviation of 7.
Yeah.
And then there we go.
Okay. What about, okay, for the, when do you put that E99 into the upper? Like,
I had it low. Mine was lower.
oh, okay.
The lower bound was the -1e to the 99.
But is it any time when we have to switch that to the upper?
Well, okay. So our calculator. Let me look at these 3 different pictures. So, like if I wanted this picture, then my lower bound would be 45, and my upper bound would be positive infinity.
Oh, okay.
If I wanted this picture here with the in the middle, then my lower is 45 and my upper is 51.
How do you type that in the calculator? That the E symbol and
it is. Let me clear this out. Okay, so -1 on your calculator. Just looking for E, and let's see. I don't think it's that one. It's not that one. Where are you? It's like exponent. EXP is usually what it says. Well, you should have the same calculator as me. Where is it? Usually above these blue. Oh, there it is. I gotcha. Okay, right above the comma.
oh, okay.
In blue, you should see that EE.
Okay, yeah.
All right, -1 EE 99.
Okay.
Yep.
All right.
Yep, and that's just all that is scientific notation. Anywho. Okay, so here's another one. This time you're shading in the middle. Do you want to do that one, or you feel good about it?
I'm okay with that. That's fine.
Okay. Here's another one. Let's see. Draw a normal curve. Okay, so you're shading in the middle here, so another shade middle. That's not too bad. Find the 80th percentile. Okay, we can look at that one. Okay, so they give us the mean, they give us the standard deviation, 80th percentile. So we kind of have to clarify, when we say 80th percentile, that means that individual scored better than 80% of those who took it, and only 20% worse than those who took it. So the phrase 80th percentile simply means the lower area is 80, or 0.8. So, so if they give me the area, that means I can use inverse norm. And then I just change the mean and standard deviation to the numbers that they tell me. And there you go.
Okay.
So that inverse, that norm, we get a lot of bang out of norm CDF and inverse norm. I mean, that's our bread and butter for pretty much most of the unit.
What about that one?
Yeah, I was gonna say, let me read what it says. Make it bigger. All right, mean incubation period for eggs is 104. Kept at 104 is 19 days. Suppose the incubation period is normally distributed with a standard deviation of 1. Okay, so a mean of 19 and a standard deviation of 1. What's the probability that a randomly selected egg hatches in less than 17 days? Okay, so it's asking about a probability, and it gives me a mean and standard deviation, so it's asking us to use norm CDF. So I'm just going to go to norm CDF. And if it wants less than 17, so 17 is the lower bound is going to be negative infinity. The upper bound is 17 in the picture. And then I just need to switch the mean and standard deviation to match this. So they said the mean is 19 and the standard deviation is 1. And so that's where they get that one. Okay, over 21. Well, that's again, we can go back to our norm CDF. And if it's bigger than 21, so that means my lower bound is now 21, and my upper bound is positive infinity. So that's 1e to the 99. And then I can keep the mean and standard deviation to be the 19 and 1. And there we go. And then the last part, or part C, says between 18 and 19. So I just go back to norm CDF. 18 on the lower, 19 on the upper. And then hit enter. And there we go. And then the last part says, would it be unusual for it to be less than 17.5? So I want to calculate the p-value for that. So that's back to our norm CDF friend. Since it's less than, that means I want negative infinity on the bottom side. And my upper bound is 17.5. And then I get a probability of 0.066. Okay. So what it's asking in part D then is that something I would define as unusual, and they're saying that 0.05 is the magic unusual number. So if it's, it's kind of like this particular event that they're describing would randomly happen 6% of the time, but I'm not getting excited unless it's 5% or less. So would I get excited? No, because I only get excited if it's 5% or less. So even though 6% is close to 5, it's not that magic I care number, if that makes any sense. So this would not be considered unusual. Does that work? Okay. So I don't know if you can tell here, it just kind of looks like we're using the same two buttons in the calculator.
Yeah.
Somehow, some way. You want to do this one? I mean.
Is that the, yeah, that's fine. That's a good one.
Okay. Make it bigger. All right. We got a mean. We get a standard deviation. Yay. What is the percentile rank of someone who is 60.1 inches tall? Okay, so percentile means what percent of the data is lower than that value. So this time they want a percent out of me, so that's where I'm going to do norm CDF. If they give me a percent, then I do inverse norm. So norm CDF, they're saying 60.1 is, I want less than that, so I'm going to go lower of negative infinity and then upper of 60.1. And then I'll just type in the mean and standard deviation they give me. So 63.9 and 2.7. Okay, and so I get, let's see, round to the nearest integer, so that rounds to about 8%. So that observation would be in the 8th percentile. Then part B, they're asking for the percentile for someone who's 70.1. So I'm just going to go back and do the same thing. Norm CDF. And so the negative infinity part stays. This time I want 70.1. And then update all those others. So I get that it's in the 99th percentile. What proportion are between? Okay, so this time it's asking for the percent. It's not, the percentile is like a whole number representation, but it's part C is asking for the exact same thing. It's just this time it gives me an upper and lower bound. So norm, okay, 60.1, 70 point, okay, so all that, and just update, and ta-da! So 90.9095, so about 91%. Would it be unusual for someone to be bigger than 70.1? Okay, so that's actually referring back to part B. So we got that someone who is 70.1 is in the 99th percentile, and they're asking for someone, is it weird to see someone taller than that? And there's only 1% of the data that would ever be taller than that. And this 5% is the magic I care number. So clearly 1% is less than 5%. So yeah, that's rare enough that I get excited about that. So that's why A is the right answer there, that it's less than 5%. So that is something that's significant, or that is something we would define as unusual on that. Any questions about that? Okay. Gotta find something that doesn't involve norm CDF.
Yeah, I guess you can go to the ones that I didn't attempt and then the ones I got wrong.
Okay. Yeah. All right. So we got a blank one here.
Yeah.
All right. So let's jump in here. All right. So this one was left blank. You get a mean. You got a standard deviation. They ask for percentile. So to determine the 19th percentile. Okay. So they're saying, what if the mean is 21 days? What's the magic number that I would expect only 19% or less to show up? So that's they give me the percent, so I want a z-score out of that, so that's inverse norm. And the area is 0.19. I'll just update, let's see, mean of 21 and the standard deviation of 1. So I would, see, round to the nearest whole number, so 20. 20 days would be considered the 19th percentile. Determine, see, part B says determine the incubation times to make up the middle 97. Okay, so if we're looking at the middle 97, then what percent would be in the tails? In other words, what I got, the big mound is 97%, so what about the other two sides of that? So that's 1 minus 0.97, gives me 3% for total between the two tails, but I want just one, I want to know half of that. So that means on the lower, let's see, determine the incubation times that make up. Okay, so on the lower end, I want 0.015. So that's going to be inverse norm with that percent, and then we'll type in all the other numbers about mean and standard deviation. So 0.015. Everything else we keep the same. Okay, so on the lower side, I get 18.8 days would represent the low number. And this is actually symmetrical, so you can just go in and subtract that from 21 and then add that to 21. So on the low end, it's 18.8, and on the upper end, it's 23.17. So that would be the middle 97% would be between those two numbers. Is that, any questions on that?
No.
Okay. Yeah, I mean, at this point, you kind of get the impression, oh, so everything's pretty much inverse norm or norm CDF. And this section that is true. I think that was the only one you actually left blank. And there's a couple.
Yeah.
Let's see. Let's go to this guy. 18 was just flat out 100% missed. All right. Let's see. All right, number of chocolate chips in a bag, approximately normally distributed with a mean. So we got a mean, we got a standard deviation. Find the 26th percentile. Okay, so we're going to go to inverse norm. And 26th percentile means 0.26% of the data is below that point. I just type in my mean and standard deviation. So 12, 62, and standard deviation of 118. And
That's it.
there's my magic number.
Uh-huh.
The number of chocolate chips in the bag make up the middle 95%. So give me the two numbers. So basically do the same thing we did a second ago. If it's the middle 95, then I want to figure out what percent is in the tails. So that means total is 5, but each tail individually would have 0.025. So I want to inverse norm the 0.025. That should give me the bottom number. Okay, and there's the bottom number.
Okay.
And again, this is symmetrical, so if that's below the mean, I just want to figure out how far the distance above the mean it is. I'm going to add, so once I figure out that difference, I'll just add it to the mean. And that's where we get, oh, that's not good. Hold on. Right. Right. Got the bottom end.
Mm-hmm.
What did I do? Okay, let me look. 155, 186. 2. It's 1493 minus the mean. Less. Oh, what did I screw up? Oh, okay. You see what I did? I didn't. The mean is 1262, so I goofed up. I didn't subtract it from the actual mean. I made up some random number that I thought was important. If I actually paid attention and add that to the 1262. Ah, there's the number. That's where they get the 14.
Okay.
Sorry, if you actually use the mean, you should get the number right. As opposed to some other random number that I just used. Okay, any question on that one?
Uh-uh.
All right. We got just a couple more here.
I have some questions about the homework that I'm working on right now.
Let's do it. Are you done?
Yeah, I'm done with this one. The sample
with that one?
proportion.
All
Yeah.
right. I nothing personal. I have found my limits of norms. Sample proportion?
Yes, it's number starting with number 6, part B and C.
Okay, I'm trying to decide how I want to take the picture here. All right. Okay, so suppose a simple random sample of 50 is obtained from a population of 30,000. It's proportional, so the probability of success is 0.6. Okay. Describe the sampling distribution. Okay, so we got that one. It's approximately normal. Now it's not going to ask this, but I love to when I do this in a face-to-face setting, I love to drill my students on why do we care if it's normal? Like, it seems like this word normal keeps being thrown in our face. The only reason why we keep having to compare this to a normal distribution, if our data, if our scenario happens to be normal, that means I can pull up the norm CDF and the inverse norm stuff that we just did about 20 examples on.
Okay.
Right? I'd like to be able to say what percent of the time I would see a certain observation. So if I can figure out a way to justify why that particular sample is normal, then I can start pulling out norm CDF and inverse norm when I have to use it. So you're going to see, especially when we talk about sampling distribution questions, someone seems to think normal is very, very important. And that's just so we can get a sense of the norm CDF part there. Okay, anyways, I digress. Okay, so it says determine the mean of the sampling distribution. Well, if that's where the point, I mean, that's just the 0.6. And then as far as the standard deviation, that's a formula?
Yeah, I got that part.
Okay.
It's just the part B.
Okay, so what is probability that obtaining x equals 31 or more individuals with that characteristic? Okay, so if I expect 60%, I mean, that's that 0.6, so I expect 60% of the population to exhibit this particular characteristic, I want to know what's the likelihood that I'll bump into 31 or more that have the same characteristic. So the first question is where they get that 0.62 from. They're just saying, you know, there's 31 people or more that I'm interested in, and that's 31 out of 50 is 0.62.
Oh, okay.
Okay, so if I expect 60% of the population to have blue eyes, and I happen to bump into 62% of the population having blue eyes, should I think that aliens are invading the Earth? I mean, is that something I should get excited about, or is that just a normal, you know, that's just, well, just try looking at another 50 set of people, you know? Okay, so I have, let's see. So we want to check and see that it's greater than 0.62. So I can go up to my norm. Let's see, well, let me look here. Try to see if we don't, I don't think we have. It's not under forest, no. Not stat, not calc. No, we're not there yet. Okay, sorry. Trying to get ahead of myself. Okay, so we're doing, trying to find a probability, which means I'm going to use norm CDF. Okay, and I am checking to see if something is bigger than 0.062. So again, norm CDF measures things in terms of less than. So as long as I understand that, well, no, we're fine. So I'm going to do a lower bound of 0.62 and an upper bound of infinity. So 1 e to 99. And then my mean in this case, since we're talking about proportions, is going to be 0.6. And my standard deviation is that sample number that we calculated, that 0.0669282. And I'm going to go back and show you another way you can do that. So you can type in the approximation, and it's going to, will be most of our decimals should match up. Anyways, so that's where we're getting the 0.3864.
Okay.
Okay. The other way to do that, same calculation. When you do the standard deviation, instead of typing out the approximation, you can actually just type in the exact. So for a proportion, I think it's NPQ. I said NPQ, right? PQ over N. It's PQ over N. So 0.6 times 0.4 divided by the 50. Let's see if it likes that. Okay, so you can approximate it and type in the approximation, or you can just type in the formula and get the exact. And notice there is a slight difference. If you look at the two numbers I have, I don't see a difference until we get out to like the 1, 2, 3.
Oh yeah, further out, yeah. 5 and 0.
Right. So like 8 decimal digits later, the fact that I was approximating versus exact difference, but for the most part, it's not going to make a difference for us. Got it?
Mm-hmm.
All right, and then part C. So that one I need to throw at the end bottom here. Okay, part C says, what's the probability of getting 28 or fewer? So in other words, I expect to see 60%. I only bump into 56%. Should I be worried? So looking at the probability of it being less than 0.56. So go to norm CDF. And our lower is going to be negative infinity. And our upper is 0.56. And then everything else stays the same from the last time. So let's see, 0.2819. That's what it looks like. Okay.
Mm-hmm.
You want to look at another one?
Yeah, I think, let's see. I think maybe 7 is the same if you can look at it, because I was having that same problem when it came to B and C. The same what we just did?
Yep, exact same.
Okay, all right, we can skip that one.
Now the big, let's see, the one difference here, and this takes a while to get used to, is we have to kind of remind ourselves of what type of data we're dealing with. So it's actually the same. What we're going to do is the same, but if you notice, they did not give us a hint on B and C that we're supposed to be thinking proportions. But that 0.79 represents an expected proportion. So I have to go in and say, well, what is 820? 820 divided by 1,000 is 0.82.
Mm-hmm.
So I have to be aware enough of what's going on that, okay, so I'm supposed to do a norm CDF with 0.82 and 0.79 as opposed to the 820. Like I'm not going to type 820 in. I'm not going to type 770 in. I'm going to type in the decimal, the percent of the observations that fit that. Let's see. Let me actually read the question. So more. Okay, yeah. So norm CDF 0.82 all the way out to positive infinity. Uh, 0.79. Let's see, might as well just clear that out. Blah, blah, blah. So 0.7.
Can you put the same 0.0099 there?
I can put in the not the populate. I'm sorry, one more time.
Can you put the answer for B in that slot?
No, because that's the answer. That's like I'm trying to get the calculator to give me that number.
Oh, okay.
So I'm just typing in the formula for the standard deviation rather than use that 0.0129, which, you know, we saw that it works. So I'm just a stickler for trying to be as accurate as possible. So that, yeah, that's they did norm CDF, and that's where they're getting that 0.0099 from.
Okay.
And so then I have to be aware for the last part that it's 770 divided by 1,000. So I have to compare that with a probability of 0.77 and compare to the 0.79. So when I do norm CDF, let's see, 0.77 with 0.79, and then everything else is the same. I'm sorry, let me pay attention here. Negative 1 to infinity. So that's negative infinity on the lower end. And upper's 0.77. It's like, I want a new question. Norm CDF is... I'm like, norm CDF robot. All right. And so there we go. That should be your answer.
Okay.
Anything else you want to look at on that one?
Let's see. Not on 7. 8.
8. Okay. Make it bigger and see. It's at least a different question. You'll find after doing an hour of norm CDF and inverse norm with me that you'll probably be a lot better at it now.
Okay.
All right, let's see. So, according to a study conducted by a statistical organization, satisfied. Okay, so the expected probability is 0.76. Describe the sampling distribution. Okay, blah, blah, blah. Using the distribution of part A, what is the probability that at least 82 Americans? Okay, so again, that's 82 out of 105. So I have to convert that into a percent. So even though they said 82, I'm not typing 82 in the calculator. In the norm CDF, I'm typing in 82 over 105. So 78%. As opposed to the 76 that they expect to see. But other than that, it's the exact same thing we did. Part B is greater than, part C is less than. You want me to do it, or?
Yeah, you can do it.
Okay. Enjoying the show. Okay. Norm CDF. Okay. All right, so lower is going to be that 0.78. Upper is positive infinity. Let's see, 0.76. I'm just going to be lazy and type in it. I'm just going to type it in.
Okay.
0.042. All right. Oh, see, it made a difference. Oh, wow. Okay. Let me go back and not type it in. Let me not approximate it. We got close. All right. Let me go back and be a little bit more exact. All right. So let's try this as exact. Let's say 82 divided by 105. And we'll make that the square root of 0.76 times parentheses 1 minus 0.76 divided by 105. Let's see if exact wins. All right.
Yeah.
Yeah. Honestly, I would give you 0.317. I mean, I'd give it to you. I mean, I understand if you're not exactly typing it in, you're not going to get the exact answer that the computer wants, but I would override that and give you credit for it on a test.
Okay.
So, do you want me to do part C?
Yes, please.
Okay. All right, this time 77 or fewer, so now we're on the lower end. 97 divided by 105. Everything else we get to stay the same. All right. That's done.
Okay.
Let me go back. You want to look at 9?
Yeah.
Okay. Looks like you're still working on it. So he says find the mean and standard. Okay. So you got the sample size thing done, and the mean is just going to be what they tell you. They expect 33%, so the mean of the sampling distribution should be 0.33. The standard deviation for that, let's see, so standard deviation would be square root 0.33 times 1 minus 0.33 divided by the sample size, so 500. So standard deviation should be that, the 0.021.
Okay.
And I don't know what else it's going to ask you, so it's about, well, actually I can look and see what the example says. I'll ask about. Okay, so then they'll ask you a norm CDF and the lower bound, upper bound question that we've done about 20 of.
Okay, same thing. Okay, that's fine. All right. And it's one other different. I don't know if it's 10 or 11. It's like a one with a paragraph. Yep, that one.
What's wrong with paragraphs?
It's too long. It's too long.
It's too long, aren't you? What you want to be a nurse, right? Yeah. So when your patient talks to you and gives you a paragraph, you listen, right?
Yes, you do.
You can't go, okay, can you tell me the problem in like 3 words or less? No.
Sum it up real quick.
You wish they would do that, but all right, moving on. So we can get to bed on normal. All right, exit polling is a popular technique used to determine the outcome of an election prior to results tallied. Suppose a referendum to increase funding for education is on the ballot in a large town. An exit poll of 300 voters, okay, so sample size 300, finds that 159 voted for the referendum. How likely are the results of your sample? The population proportion in favor is actually 0.49. Okay, well.
Do you do it? Hold on, is it just divided by the 100,000?
Well, the 100,000 just is there just to say that there's a lot of people in town. So the fact that they talked to 300.
I'm sorry, the 300. That's what I meant.
Yeah, it's the sample proportion, or p hat is the number of successes divided by how many people they talked to.
Right.
Okay, so they talked to 0.5 or 53% said they'd vote in favor. The question that they're asking, whether or not it's phrased like this, is they're saying, hey, we've talked to all 100,000 people, and we know that only 49% of them like this thing, that like this referendum. So the fact that you talked to 53% and got them to say that they liked it, should politicians be nervous that something's going to pass? You know, they expect 49, they saw 53. Is that something they should be freaking out about? Okay, that's what the intent behind the question is. How likely is 53% when I expect to see 49%? Okay, so this is a norm CDF again. So go to norm CDF. All right. I saw, let's see, how likely is us in favor of, okay. So I saw 53% say yes. So I want to know what's the likelihood that I would expect to see 53% or greater given that I expect to see 49%. So my lower bound is going to be 0.53. My upper bound is going to be infinity. The mean, I expected 49%, so the mean should be 0.49. And then the standard deviation is based off that expectation. So 0.49 times 1 minus 0.49 divided by 300. Okay, so then I'm going to hit enter. And I get a probability of 0.083, so about 8%. So I would expect to, so if I go out and I talk to 300 random people, I would see what I saw about 8% of the time. So should I be freaking out or not? And the answer is no. Typically 5% is the get excited for number. So the 8% is not enough to get excited for. So anyways, it's just a norm CDF question. Does that work?
Yep.
Okay.
About it.
And I think 11, I suspect it's probably the same thing. Oh, it's a sample size question. Oh, goody. It actually asks something new. That's cool. I kind of want to do this one now. Or do you want to do it on your homework without my help?
No, you can go right ahead.
Well, Jessica, it sounds silly, but if my personal feeling is if I do the problem for you, you just watch and you don't really learn anything. So the next time you see it's on the test, how do you know if you know it? You know what I mean?
I have to go through and do it.
That's right. That's right. And it's a lot stronger a feeling when you get scared and have to try it your first time on your own. But quite frankly, I've done norm CDF about 20 times now, so I'm just happy to do something different. Okay, so there is a formula for this, believe it or not. There's a formula for everything in this class.
I see.
Yeah, so I'm just going to jump right down here. Oh, that's lame. Okay, so here is our magic formula. All right, so take my calculator out. I want to take 10 divided by the 0.2 times 1 minus 0.2. See if I did that right. I got enough parentheses. Okay, now I do. Okay, so I need to talk to 62.5 adults. They talk to 50. So I need to talk to 13 more people. That's it.
Oh.
You want me to do part B?
The part, it's the same thing, just doing, instead of the 0.2, just put 0.25.
Yes, ma'am.
Okay.
And then subtract from 50 and just round. I mean, hopefully you can round. So.
Okay.
So yeah. All right. Anything? that was at least it was different. That was exciting.
That is about it.
Yeah. All right. Anything else you want to talk about?
No, I think I'm okay now.
Okay. Yeah. Anytime you need help, I mean, just email me, and I don't mind throwing. You know, I wish more students would say, "Hey, do you have time for me?" And you know, that's fine. You know, not a lot of students figure this out, so I'm glad you figured it out. And now that we have about a month left, feel free to abuse it.
No, I know.
I'm gonna do an online. I'm trying to think about what our test is. So is our test next week?
Yeah, next week.
Next week. All right. So probably Tuesday night.
Tuesday. Okay.
Is what I ain't said nothing yet, but I'm gonna say Tuesday night. So I'll put that in the calendar, and Tuesday night about this time I'll do a class-wide review. But if you're trying to knock the final out early, you're more than welcome to say, hey, can you meet for an hour and we'll go through calculator screens. But
Oh no, I think I'll be doing that on time.
Gotcha. All right. Well, I will tell the computer to not lose the record. So I'll send you an email with the link to this video.
Okay, thank you.
Go back and watch me do norm CDF 20 more times in a row.
Yeah, I sure will. Feel like it's down pat.
All right. I will talk to you later.
Thank
you. You should get an email from me in the next 20 minutes.
Okay, thank you so much.
Have a good night.
All right, you too.